All right, welcome everyone. Welcome back to the Dream Seminar. Thank you all for joining. Today we have Sam Burden, and David's going to give us a nice introduction of Sam. Before he does that though, I just want to remind everyone that there are office hours with Sam where you can ask all of your burning hard questions for him after his talk from 5 to 6. So with that, I'll let David take it away.
Yeah, welcome everyone. I think you're in for a real treat today. Sam is a alum of our lab, and we're very proud to have him back. He originally did his undergrad at University of Washington in Seattle, where he's now a professor back in 2008. But mainly we celebrate that he did his PhD right here in electrical engineering, computer science, and then did a postdoc here as well. And actually, I think you ran some of the research in biology actually for a little while there.
Well, I collaborated with Professor Bob Full, who's on the line.
Fantastic. So we'll see a range of topics from theory to bio. Buckle yourselves in because you're in for a wild ride.
Okay, thanks so much, David. Thanks everybody for attending today. It's a real pleasure and an honor to be able to come back and speak to you anyway from the comfort of my bedroom. Yeah, I'm really excited to be able to share this work, which is it has these kind of two themes that you'll see aren't totally unified at the moment, but we've been pushing hard on both of them, and I think that unification is on the horizon. So the two themes are the contact-rich dynamics of robots with legs and hands and arms and things like that, and how to model and manipulate, or how to design humans in the loop with control systems. The kind of fun thing at this point, so I'm in my, I started in my faculty position in 2015, and at this point, now I'm presenting work almost entirely with a few small little sidetracks that came out of my work with my PhD students. So it's a real pleasure to be able to present this stuff to you. My understanding is that this can proceed somewhat interactively, so I'm totally open to that. My understanding is that you're able to unmute yourself if you'd like. So feel free to interject at any time. I don't have to get through all the material. And I've even been told that there's a possibility to run long if necessary. I'm going to try to keep to the schedule, but yeah, I'm happy to kind of dive in. Let's see. Oh yeah, and in the Zoom era, I think it's kind of nice to provide link to slides that has all the videos embedded, or just lets you kind of skip around non-linearly. So if you want to, copy or screenshot this URL, and you can grab a copy of these slides so that you can follow along or catch up or anything like that. So the leaping off point for this talk is the observation that our interaction with the physical world is increasingly mediated by machines. And importantly, these are not the simple machines of classical era. These machines are intelligently learning and adapting to us and the complicated environments that they're interacting with. So 3 little vignettes that I think are really exciting and indicate the potential of these kinds of things to impact the way we live and the way we work. Robot-assisted surgery is one of the big accomplishments in this area. The initial patents were held by Intuitive Surgical. They built the Da Vinci robot, widely deployed it. Over the last couple of decades, it's significantly improved certain kinds of surgical outcomes, and the reach of this just continues to extend. But it's an exciting idea that through highly trained people, experts in their field, through the assistance of machines, could improve our health in the way they interact with us. Another recent kind of landmark accomplishment is the ability to directly read neural signals from motor cortex and use it to control something like a robot arm. This came out of, Schwartz is one of the key people out of Pitt, but it's a big collaboration. And if you haven't seen this work, so Jan here suffered a spinal cord injury a decade or more ago, where she lost full motor control of her body from the neck down. And the kind of high-level takeaway from this work is, with this type of device, she's able to perform an activity of daily living like feeding herself that probably most or all people on this call just take for granted, among many other facets of life. So the potential for these kinds of interfaces with machines to dramatically improve quality of life for people in disease, in injury, in neuropathological disorders is kind of completely untapped at this point. And then the final example I have is out of Steve Collins' group when he was at CMU, where he built a completely passive ankle exoskeleton that reduced the metabolic cost of walking by a couple percent. So completely passive. There's no computer, there's no motor, there's no battery. It's just a clever spring clutch mechanism, and it's kind of exquisitely tuned to human biomechanics, and it reduces metabolic cost of walking by a couple percent of healthy subjects, unimpaired subjects. And you hear this statistic, you're like, a couple percent, big whoop. But when you think about the fact that one of the leading theories of why we evolved to become bipedal is that we literally would walk our prey to death. So we were, evolved to be pretty efficient walkers. Then a couple percent improvement over that with a, again, completely passive mechanism, I think just speaks to the untapped potential for devices to not just, help us in when we have, problems with health, but actually just enhance our interaction with the world in all kinds of daily life. And the other lens I want to take on this is that there are a lot of systems that are going to become fully autonomous. Cars seems inevitable, seems like it's just around the corner almost. But there are many systems, these included, where a variety of considerations that are extra technological. They're not technological limitations necessarily, that will ensure that people will remain in the loop with control systems forever, basically. And so I'm really interested in these kinds of regimes, not the cases where we could fully automate out. So those are big problems and big areas. For the purpose of this talk, I'm going to narrow the focus quite a bit, and I'm going to focus on robot teleoperation. The nice thing about robot teleoperation compared to some of these other examples is that we have a very clean division between the human and the robot. And so as a control theorist by training, as David mentioned in my introduction, I've studied formally, I've studied control theory for all my degrees, and then I try to collaborate and apply the methods and develop methods to apply them to physical systems. But as a control theorist, it's really nice to have like a clean interface that I can draw and a nice block diagram that I'll get into in the second half of my talk that connects the different subsystems in my overall, interactive system. So in robot teleoperation, on the off chance you're not familiar with this, the paradigm is that a human will have one or more kinds of devices that it uses to provide control signals that are passed to the robot and literally used to choreograph and guide the robotic system around. And then that robot in turn passes back some kind of sensory signals. It could be just a camera, or it could be haptic, or it could be neural stimulation, or it could be VR, AR, or a variety of different possible modalities. So this is a very broad area. There's a lot of different possible regimes that you could, that people have studied robot teleoperation that you could imagine applying it in. So again, to put a little bit finer point on it to motivate some of my work, I want to think of a kind of extreme regime. Let's think about a teleoperated robot firefighter. Now, I'm speaking to a group in California, up in Seattle. I just got to enjoy we suffered from the same kind of, chronic smoke from wildfires and just the danger to property and human lives that you folks have suffered from all summer. And this is a real problem, and it's only going to get worse with climate change and kind of human encroachment in the natural environments. So, what's kind of wild, what's kind of crazy if you look at it somewhat objectively, is that when something like a fire happens, the first thing we do is we put more people in harm's way. We put first responders, very, courageous and valiant people, go and directly put their lives on the line to fight these things. So wouldn't it be nice if we could just pull the person out of danger and send in a robot instead? Now, I'm going to do a little bit of an aside, and I don't want to dwell too much on bashing on this kind of robot bashing. Now, if you want to send in a robot, it's not realistic that the robot's going to be fully autonomous, I think, anytime soon. In this kind of extreme, challenging environment, scrambling over rough terrain, over boulders, maneuvering around trees, digging up bushes, digging trenches, it's just not plausible. So these are, this is the bloopers video from this very famous DARPA Robotics challenge from a couple years ago. I don't want to completely trash the results of this. I mean, there were some really remarkable achievements. Once the robots were able to get within reach of some kind of object to manipulate or tool or valve to close, they were generally able to coordinate, 32 degrees of freedom or something like that in an Atlas robot to twist a valve, drill a hole, saw a hole, or something like that. It's really, really remarkable integration of, full robot stack from hardware up through software and processing and planning. But if I return to my application, it's not something that I'm going to assume is going to be fully automated in any kind of foreseeable future. And in general, it's we're going to have people in the loop, we've got to be careful about it. So I have a couple of vignettes here from the literature and from kind of daily experience. This has been an observation that the aerospace people have worried about for decades. So there's this phenomenon there called pilot-induced oscillations, where if you're designing a high-performance aircraft, you actually want the passive dynamics to be marginally stable or maybe even a little unstable, because that gives you maneuverability. You know, a 747 or something like that is very stable, which means it's not going to be doing backflips and, you know, evading attackers and things like that. But the problem is that if you're then relying on the pilot to close the control loop and stabilize the system, and if you fail to take into account the basic neuromechanical delay that people have just because they're people, they can't help it, then they can actually introduce delay that causes oscillations that can lead to crashes. And this has happened for multiple test aircraft that pilot-induced oscillations were ultimately determined to be the cause. And just think, you're working at Lockheed or Boeing or whatever, and you're working on 5-10 years on a couple $100 billion project to make the newest experimental aircraft, and you forgot to take into account the fact that people have a characteristic delay of, you know, 100 milliseconds or something like that, and then you put the pilot in the plane and boop, they have to eject and the thing crashes. So that's just something that they've taken very seriously, and they have a variety of methods to model and kind of anticipate and mitigate. A more recent example, so I actually just got a brand new car because I'm an assistant professor, so I'm rich, right? It was time. And this car came with, I haven't had a new car, my last car was a 2011 or something like that. And so the big innovation in the last 10 years are these enhanced safety features. So these are things that try to keep you in the lane, so the lane keeping assist, try to keep you the right distance to the car in front of you, so they're adaptive cruise control. And the car like dings and bings and jerks the steering wheel actually in order to stay safe. And the first time you get in there, it's actually quite, if you don't have a lot of experience with this, it's actually quite alarming. And indeed, there was a funny, to me, kind of amusing study from 2013 by an insurance industry, like, you know, conglomerate reporting company, where they found that actually statistically, you were more likely to be in an accident if you had some of these features in your car. So basically, you know, it was one company. This wasn't a big study. This might have been a statistical anomaly. It might be the kind of thing that we just, as a society or as users, have to get used to over time. But anyway, statistically, you were more likely to be in an accident if you had these quote unquote enhanced safety features, which, by the way, cost a couple $1,000s to get installed because they're complicated sensors and computers and all this stuff. I think the situation has changed. Actually, anecdotally, my monthly car insurance payment for the same level of coverage on my much more valuable car is the same price. And the reason is that the price to insure the value of the physical artifact went up a lot, but the cost to have the liability coverage in the probability that I get in an accident went down a bunch, and it actually just like equaled out. So evidently the insurance industry has figured out that these things are actually helping. But the point is that if you fail to take into account how people are going to respond, then you can get, you know, really catastrophic outcomes. So returning to this this robot teleoperation kind of sensorimotor loop that I pointed out at the beginning, the overall theme for this talk, the motivation for the work in my lab, is trying to answer this question: how do we enable people to learn and control contact-rich dynamics of robots that are out there roaming around in the world? So the talk's going to proceed in two parts. First, I'm going to talk about some of our work trying to characterize an intrinsic mechanism for stable, robust, contact-rich robot dynamics. And then the second half of the talk, I'm going to cover our work trying to characterize what the dynamics of people are in different feedback control loops. So the first bit I'll dive into are these contact-rich dynamics. And again, and if you, especially if you came late, I'm happy to take questions anytime. So if you'd like to unmute and ask questions, feel free. Because I talk fast and I can kind of steamroll over if I'm not kept at right pace. Okay, so let's dive into these technical details. So if you haven't thought about this before, then I want to first observe that the dynamics, these contact-rich dynamics, are kind of fundamentally different flavor than hydro and aerodynamics. So even though hydro and aerodynamics are very complicated, they're governed by this nonlinear PDE, Navier-Stokes equation, that can have all kinds of complicated turbulence and eddies and blah, blah, blah. At least there's an equation. In the aerodynamics side, there's literally not a fundamental constitutive theory the way there is in hydro and aerodynamics. Even if we wanted to, we don't know exactly how to, set up the FEM, the large-scale simulation model, to predict what happens when something wild like a lizard leaps or a robot leaps or something like that. And a key thing that I want to observe here, this term that I kept on throwing around, I just want to ground it a little bit better. I'm talking about contact rich. What I'm talking about is the observation that the dynamics of a legged locomotor change dramatically when their legs are in contact with the ground relative to when they're not in contact with the ground. So that's what this contact term is referring to. And so, as I said, I'm a control theorist by training and by, attitude and view of the world. So when I look at these systems, the first thing I try to think of is, okay, what's a reasonable model for what's going on? As I said, there isn't really a fundamental constitutive model to start from, so we have to start kind of guessing. And a class of models that I've investigated since I started as even before I was a PhD student, when I started research in legged locomotion, are these kind of piecewise defined models or hybrid system models. Now I'm talking to a group at Berkeley. This seminar is the Citrus People and Robots seminar, but it's also the Center for Hybrid and Embedded Systems Technology. Okay, so I probably don't need to tell you the whole hybrid system story, but so what I'm going to do is focus on specifically how the dynamics look for the class of systems that I'm interested in, which are mechanical systems, robots that are interacting with terrain. So the way these models are going to work is I'm going to talk about there's some number of limbs a robot can have, i.e. potential points of contact. And associated with each point of contact are non-penetration constraints. So my foot has to be above the ground. And then as a function of which feet are on the ground at any one time, the dynamics are kind of fundamentally different. I mean, there might be even it's very common that legged robot controllers actually try to sense or determine the contact mode and then do something different based on the contact mode. It makes sense because, for instance, if your legs are light, then when you're on the ground, you have to apply forces that are on the order of, moving your body. But when legs are in the air, the forces that you have to apply are on the order of, the mass of your limb, which is a lot less. So sensing the contact mode makes sense. But even if you weren't sensing that, the dynamics do depend on the contact mode because you get these reaction forces that prevent penetration with the ground. So when your foot hits the ground, you have to have some force that comes up to keep the foot from going through the ground, according to the model. This is a simplistic model, but that is kind of expressive enough for some situations of interest. And then finally, if I'm going to say that the ground cannot be penetrated, then I'm going to have to do something if my silly foot is hurtling at the ground and impacts it with some negative, some velocity that's giving me a negative Lie derivative of that constraint function. And so the simple-minded way that we're going to talk about that is that the velocity instantaneously resets. So there's a quote-unquote impact law that could be a nonlinear function of configuration, but it's a linear function of velocity, at least in this formulation of the mechanics. Okay, so we have these kind of piecewise dynamics. That's the key thing I want you to take away is that, when we have a certain set of limbs on the ground, then I'm basically just F equals ma. And then when I have a foot that's impacting the ground, I have to do kind of momentum balance to basically like zero out the part of the velocity that's penetrating the surface and maintain the other part of the velocity. In case you're a real like Lagrangian dynamics geek, I'll say just to preempt some questions that I'm mostly for simplicity going to say kind of general statements about the frictionless case. It's also pretty easy for me to handle the non-slip case, but I'm not going to say anything about friction models or transition from stick to slip, because as we'll see, it's a source of kind of a problem in the dynamics that I want to avoid for very specific reasons. So to give you a little bit more intuition about what these dynamics actually do in practice, and then also kind of set things up so that I can explain my results a bit better, I want to show a couple pictures. So, here's the simplest system that I can think of that fits this class. It's a hopper, right? So if I was in person, I would let you enjoy watching me jump up and down in place. For now, you're just going to have to imagine. And so what does this system do? When the foot is on the ground, it pushes up and then the foot comes off the ground and the leg contracts and then it pushes back down. So if I excite it with a periodic input, I get this kind of periodic, excitatory hopping motion out. So visually, what you should think of is that there's some initial, I could start from some initial position and velocity, and then I follow the dynamics F equals ma until my foot hits the ground, at which point my velocity has to change discontinuously. The foot velocity has to go to 0, otherwise it'll go through the ground. And then I'm reset, and then I kind of continue going as before and end up at some final condition. Now, you look at this, you think about my description of the dynamics, and you look at this picture and you see these jumps in state, these discontinuities, and you think, gosh, this looks bad. Nonlinear system, or smooth nonlinear systems are gnarly enough. So how am I going to handle a system that has discontinuities in it? And the kind of surprising thing, although it makes some sense on reflection, is that in fact, these dynamics, when I have only one constraint that's activating or deactivating, or more generally, if I know the sequence of contact modes, I've kind of mode scheduled or decided on which sequence of footfalls and contact configurations I'm going to go through. Actually, even though there are these discontinuities in the middle, the overall flow, so the final state, Q and Q dot at time t, actually depend differentiably on the initial state, continuously and differentiably, and not some bizarro generalized notion of differentiable, which I'll actually get to in a bit because that's our work, but totally classical differentiability. This has been known for a really long time. Of course, it was the Russians that figured it out first in the 50s, as with everything worth proving. And then, a number of us, myself included, have reproven or rederived this result in various contexts over the years, but this is just like a really well-established result in this area. So although it might look surprising, intuitively, what you should think about is, okay, if I perturb infinitesimally in some tangent direction, so in like the red direction or the blue direction of this subspace, then of course there's some jumps that are happening here in the middle at this impact time. But if I look away from impact times, then the final state will vary differentiably with respect to the initial state. And classically, differentiably means that, I perturb in red or blue direction in the same initial subspace, and I end up in the same subspace at the end, but, possibly kind of expanded or contracted.
I have a quick question.
Yeah, please.
So can you elaborate a little bit more on what it means for the context sequence not to change? Does that mean that like I'm assuming that like these mode sequences, especially if you're controlling the system, have to be like planned or somehow determined? So is it that like given a fixed mode sequence, which never be like replanned and like changed, then this theorem holds?
Exactly.
Okay.
Yep, that's exactly right. And then maybe I'll kind of anticipate your question or the next couple questions you have with my next couple slides, because yeah, my focus for a number of years has been, what if that sequence can vary? What happens in particular at the transitions between different sequences? And this is motivated largely by observations from biology and then consequently from bio-inspired robotics, that a lot of behaviors of interest can have multiple limbs activating, contacting or releasing contacts simultaneously. So if I think about the alternating tripod of the cockroach or the robot that it inspired, Rex, then there are 3 legs on one, 3 legs that are synchronized and other 3 that are anti-synchronized, and 3 legs touch down at the same time and lift off at the same time, touch down at the same time, lift off. Or if I think about a quadruped like the bounding cheetah from MIT here, then the front 2 legs touch down at the same time, then lift off, and the back 2 legs, and so on and so forth. But of course, that's just nominal, right? So that would be to kind of bring up your question again, Andrea. That would be the sort of plan, the initial plan, that I will go from in the case of Rex, I will go from unconstrained to 3 legs to unconstrained to different 3 legs, right? But of course, if the robot gets perturbed at all, or it stubs its toe, or it degrades at all a little bit, or if there's any kind of noise or uncertainty, anything whatsoever, of course, if I get perturbed, then my feet are going to touch down in a different contact mode. And so I'd like to be able to reason about and get some handle on what happens to the system if it gets perturbed off of its nominal contact mode sequence. Unfortunately, what happens in general is really bad. So in particular, if I build my robot the way that we usually build robots, this slide was actually kind of very deliberately chosen to have one robot built this way, the cheetah, and another robot, Rex, that's not built this way. But anyway, if I build my robot the way we usually build them, which is out of, what do? I go to McMaster and I order a bunch of rigid struts and I bolt them together with rigid pin joints, and I get this kind of I'm going to call it a rigid kinematic tree, okay? Then the problem is that as I change the contact mode sequence right at that interface, things go really badly. In what sense do they go badly? They actually rip apart. So I actually get discontinuous dependence on initial conditions. This is not our result. This is an observation that's been in the literature a couple times. And just my favorite couple of vignettes that sort of illustrate this. So for instance, if I had a rigid object like my steel water bottle, and then if I had a rigid kinematic tree like a hand. Now, granted, my hand, because it's squishy bio hand, is not a rigid kinematic tree, so you're going to have to use your imagination. Then theoretically, the results say the following. If I have some number of digits in contact with the rigid object, and then another digit comes in and impacts with non-zero velocity, some subset of the digits that are currently in contact have to pop off but which exact subset depends on who you trust for your impact law, which 17th century French mathematician. So is it Legendre or Lagarde or Poincaré or who? And so my view on this is that this rigid kinematic tree construction, when cast into the modeling paradigm that I'm using, this hybrid modeling paradigm, although this really has to show up, it really in any kind of invariant, doesn't really depend on the modeling paradigm, but I can show you exactly how it shows up in my modeling paradigm. I really think of this as like a model inconsistency. This is a bad feature of the model. This is not a place where I want to rely on my model. So I'm interested in what would it take physically, what is the minimum change I would have to make in the way that I design my robots and therefore model them that would make this problem just go away. And the specific mathematical obstacle that I'll try to remove is the fact that if I'm a rigid kinematic tree and two contacts are activating at the same time, then if I were to apply the impulse that I get by first activating one and then the other and then doing it in the other order, I get different answers. That's the crux. That's where this issue arises, is exactly at that point. I get this non-commutativity of these impact laws, and so then I get inconsistencies in my outcomes and stuff sort of shears apart. So what I need to do is I need to impose some mathematical condition that makes it so that these two functions commute. I could talk for a long time about different ways to get at this. Mathematically, what I need is that the constraint normals are orthogonal with respect to the inertia tensor, like the Riemannian metric associated with the mechanical system. Physically, what you can think is either my limbs are not, my hips are not sort of rigid bolted things, but they have some kind of shock mount, so some kind of viscoelastic dampery thingy going on there. Or alternatively, and this is something I'm exploring with one of my newer PhD students, if the limbs are light enough so that you can essentially treat them as massless, then you won't have any issue. The key thing is that you can't have the impact of one foot change the velocity of another. And in a rigid kinematic tree, that always happens. And so you need some way to kind of break that rigid coupling, that rigid propagation of shocks all the way through the mechanism. So if you do this, then you get a much nicer picture. So initially with these rigid limbs, I get, I could perturb in the red direction or the blue direction off of the nominal black trajectory, and I can end up in completely unrelated different parts of state space. Formally, what happens is the hybrid system flow is a discontinuous function along this black trajectory. So that's not good. Discontinuous functions are not very fun to work with. Hard to approximate them, hard to take derivatives with them, things like that. So what we showed is that if you can decouple the limbs in this formal way that we talked about, then in this modeling paradigm, I actually recover continuity and a special new kind of differentiability with respect to initial state. So the two branches come together, so that's nice. And now if I perturb in the red direction, there is a first order approximation of how the final state varies in that direction. Or if I perturb in the opposite direction, blue, there is a first order approximation in that direction. However, that overall first order approximation, that overall generalized derivative operator is not linear. It's piecewise linear. So mathematically, what we get is that if I impose this decoupling assumption, then I get a hybrid system flow that is continuous and piecewise differentiable in a certain technical sense that we've used previously on kind of more abstract dynamical systems, and was originally developed by the nonlinear programming, like the non-smooth optimization community, to study how stationary points vary with respect to problem data. So it's a really well-developed kind of theory. There's a really nice whole calculus associated with this. So we basically were the first to apply it to understand dynamics of contact. So then now I want to apply this result. This is kind of a cute abstract result, but I want to give you something, kind of concrete to take away from it, something you could do with it potentially. So I want to answer a question. Okay, now I have trajectories vary continuously. So do they get further apart? Do they expand? Or do they get closer together? Do they contract? So is my system kind of stable in some sense, right? And so to put a finer point on it, with respect to some distance metric, if I start at some distance away, do I end up closer or further apart? Now, in order to answer this question, first we need to talk about what I mean by distance, because we have a system where I'm kind of flowing along, and then all of a sudden at some point, one part of the trajectory goes into one contact mode, resets, and the other one goes into a completely different. So how do I talk about whether they're close or far? So work that I did at Berkeley, so this is the one callback to Berkeley work, said, you know what? This actually isn't such a big deal. If you make the following just fiat, just you impose this condition on the system. You say, look, if I have a state of my dynamical system, like the robot right before the foot is impacting, so the foot is at zero height and negative velocity, and then immediately it resets to another state of the system, then those aren't really different states. At the very least, I shouldn't say that they're any further, that the system's gotten any further apart, right? Seems like a sensible enough thing to say. Now, in order to make sense of this, in order to unwrap this definition and kind of get a reasonably well-behaved distance metric, you have to do some topological violence, right? So I can't impose this condition and stay in my original, extrinsic state space. So what we did was we said, look, let's just quotient by the reset map. Let's take a topological quotient, and then let's metrize that quotient. And so we'll start from this as the basic building block of the metric, and then we'll kind of grow it out from there and make it sort of self-consistent, satisfy all the properties of metric, things like that. And indeed, that worked out. So this assertion, under appropriate hypotheses on the hybrid system and things like that, actually gives you a reasonable topological quotient space, and it's metrizable, and the kind of natural metric you would want to define on it is defined. I'm really proud of this result, and it's actually critical for the thing that I really want to show you, which is new work. So I just have to kind of do this quick callback, but really this isn't the whole point of the talk. So now that I have my metric in hand, now I can talk about whether things are getting closer or further apart. And the technique that we're going to generalize was developed for smooth nonlinear systems, and it's called contraction analysis, or more specifically, infinitesimal contraction analysis. It's a really cool idea. There's a very famous paper by Lohmiller and Slotine. However, this paper isn't the first to really prove the results. They just have kind of it's almost a survey, like it's just a really nice summary of some of the basic insights and facts and things like that. Of course, it was the Russians, Krasovsky, that originally did this, 50 or 100 years ago or something like that. But anyway, good. If you want to get started in this area, Lohmiller and Slotine is a nice place to start. And the basic idea is the following. So in classical smooth dynamical systems, I can talk about a smooth vector field, a continuous time system, or a smooth map, right, discrete time system. And so I'm going to kind of do the parallel constructions here, and then I'm going to mash them up and do the hybrid case, right, where I have a mixture of both in a moment. And the flavor of the statements are the following. Instead of looking at this nonlinear vector field or map, which is hard, right? Smooth nonlinear functions are complicated. Instead, what you do is you linearize. And then you say, okay, infinitesimally, are things getting closer or further apart? So if I were to perturb off of one trajectory, does that perturbation grow or shrink according to the variational dynamics that govern the system? Those variational dynamics are determined by the linearization of literally the Jacobian of the vector field function, or the Jacobian of your reset map function. And the way I'm going to quantify do they get closer or further apart is I'm going to look at eigenvalues of these. So I'm kind of blithely putting these conditions up here. Of course, for this theory to work, you can't just linearize at a point. This isn't a linearization around an equilibrium, around a limit cycle or something. This is, you have to check this condition everywhere. So I have to check, this isn't one inequality, this is an uncountably infinite number of inequalities. So that's a big ask. It's a lot to ask that a system has this property. Now, interestingly, if you allow yourself freedom in choosing the metric, then it turns out there are kind of converse results, that if your system does kind of have a nice stability property, then it is contractive with respect to some metric. Good luck finding the metric. But anyway, we approach it more kind of constructively, like, hey, this is a stringent condition to satisfy, but if you can ensure it by hook or by crook, you get a really strong notion of stability. So the stability notion you get is that the distance between all trajectories decreases at an exponential rate. So basically, initial conditions are forgotten exponentially in time. And so this time dependence of the system can be thought of as an open loop kind of feed forward external input that you're applying to the system. And what this says is that it doesn't matter what input you apply, all trajectories are going to converge to one another. So if you apply a constant input, you get a stable equilibrium. If you apply a periodic input, you get a stable limit cycle. And if you apply an arbitrary kind of aperiodic input, then you can get all trajectories converging to whatever kind of arbitrary motion the system actually performs. So again, really stringent condition, not automatic or obvious that any particular system would satisfy this or how to verify it, but if you can verify it, it's a really strong, nice property.
Quick question. Can you give me any intuition for what kind of systems have this property?
Yeah, definitely. So I'm going to do that, though, after I tell you about the hybrid generalization. But basically, I'll preview spring mass damper, an example. Okay, so I want to apply this kind of method to my piecewise defined systems, and I have all the ingredients, right? I have continuous time dynamics, I have discrete time dynamics. So it feels like, hey, naively, what if I just apply those conditions, from the previous slide to both of those separately? But of course, that's not really fair, because these aren't independent dynamics, they interact, right? The the time at which I apply the reset is determined by the forces that were applied through continuous time to get my foot at the constraint surface. And then, the state that I reset to, the velocity I reset to, determines where I'm going to end up according to the next flow of continuous dynamics. So I have to look at how they interact. I'm going very slow today for some reason. I'm not sure why. So I'm going to skip this slide and just jump to the conclusion that we have to consider an augmented version of the linearization. We have to consider how the discrete and continuous interact. And I'm really happy to talk in more detail about this. Of course, it was the Russians that figured out that this was the right operator, and then we apply it in this context. And so our result says, look, if you're contractive infinitesimally in continuous time and discrete time, but this is not the linearization of R, this is this special matrix that was on the previous slide that I completely skipped over, then you get contraction. So all trajectories converge toward one another. Where they converge to depends on the input you apply. And I'll note that here, the distance I'm using is my crazy, intrinsic distance metric that I obtained by doing topological violence to the state space of the system. And it's only with respect to that intrinsic metric that the system could have this kind of infinitesimal property. We have our own sort of converse or necessity result of our own in the paper. And so an example of the kinds of systems that have this property, so definitely not rigid limbs, right? We already talked about, you don't even get continuity, so you can't even start this process. Surprisingly, at least to me, if I do a spring damper, that's not enough because of the impact. So on its own, if this was a simple harmonic oscillator that was never undergoing impact, that system is infinitesimally contractive in continuous time. But somehow the discrete and continuous time dynamics interact at impact so that this alone, the discontinuities in the force that are caused by the damper cause the system, the dynamics to become expansive at impact. So you're not strictly contractive. And so what we have to do is talk about viscoelastic. What is viscoelastic? The mechanical engineers, i.e. Tom Libby, who's also a Berkeley alum, explains to me that viscoelastic can mean put a spring in series with your damper, a stiff spring in series with your damper. This system overall can be made to approximate the original elastic one, but it has the appealing property from my perspective that forces are continuous at impact because this spring smooths out the force production in the damper, which is honestly a little bit more realistic. Like dampers in reality are fluids in a sealed chamber, and they take time to build up force and blah, blah, blah. So it's not, a complete physical fiction, but it does, make the dynamics a little more complicated. But that's an example of the kind of thing. So where we want to take this is be able to show that, a much more interesting robot than just my hopper is contractive so that we can then, control it with these external inputs. Okay, so I finished part one. The takeaway is that we have this new way of characterizing, intrinsically stable contractive robot dynamics. Part two is on human sensor motor learning and control. It's going to be a very abrupt change, and I can do it in 13 minutes, which is what I have left before 5. I can't do it in less than that. So I'm going to do it, and then I'm going to end at 5, and then happy to take questions at that point. So again, the setup that we're looking at is robot teleoperation. Specifically, we're standing on the shoulders of giants. So we're building off of these decades of work in the aerospace industry. McCruer is one of the big names, where they would sit pilots, so highly trained experts, down at a console, kind of primitive by today's standards, but really impressive by the standards of the day. You have a little joystick, so you have a one-dimensional input, manual input, and then you have a little visual display, literally like a hacked O-scope or something like that to draw a little squiggle on the screen. And the task is, so we have the input from the person. So you have to decide which is your input and your output. We talk about the human providing the input to the machine, and then the machine displaying an output to the human. So it's input output from the machine's perspective, not the humans. And then to be able to have some, experimental variability in the system, we have a reference we're telling them to track, and then a disturbance that we're kind of subliminally or not, we're kind of overlaying on their input and asking them to reject kind of implicitly. So as a control theorist, I look at the system and I say, okay, what's a reasonable mathematical model? And I would like to be able to draw things out in a nice block diagram picture, right? This block diagram picture conceptually describes that the human sees a reference and they see the error between the reference they're trying to track and the output from the system. They produce an input U that's corrupted by this additive disturbance before being processed through my machine dynamics. Like these are like my vehicle dynamics or my remote robot dynamics, right? But I want to point out and emphasize that as a control theorist, this is not just a pretty picture. this is actually math. Like this is actually equivalent to a collection of equations that, especially if each of the subblocks in here are linear time invariant, can be manipulated algebraically to get really powerful conclusions and insights. So in particular, I want to answer the question, what's in the box? Like what's going on inside the person? What are the different kind of sub-processes? And so specifically, we again, build on the shoulders of giants. We adopt this view that inside the human, they might be building up a model of the machine they're asked to control, and then doing something with that model, kind of sensibly, like inverting it. And the reason that we like this theory, it's pretty popular in the motor control, kind of sensor motor control, neuroengineering community. And it has really nice, strong parallels with control theory, concepts from AI, reinforcement learning, things like that. And one tweak I'm going to put on this is that whereas in the motor control people will talk about inverse models, control theorist, I talk about feed-forward model. And as we'll see experimentally, the feed-forward model is not exactly the system inverse. So indeed, it's nice to have a different term and a different symbol to be able to represent this concept of the transformation that the human uses to take the output they want to track and produce the input they want to feed into the system in the absence of any error. So going back to my block diagram, what I'm essentially hypothesizing is that inside the box, there are these kind of parallel pathways that sum, where the reference gets processed by this feed-forward controller, and the error gets processed by a feedback controller, and those superimpose to produce the human output. And you might think, wow, that's a lot to ask. You want a human to be a linear time invariant system? Like I remember my signals and systems class or my linear systems class, and that seems, very unlikely. I feel like a nonlinear system most of the time. What's wild though, is that if you plop a person in a chair and you ask them to do this kind of task and you make the dynamics they're tracking through linear, then over a pretty broad range of references they have to track and disturbances they have to reject, they do behave like a linear time invariant system. And that's something that we can experimentally test. How linear of a transformation is the human, or these, how well do we get, how much traction do we get by assuming linearity, estimating feed forward and feedback components, and then predicting what people do as a consequence. And it does pretty well. So what's really powerful, again, about this control systems modeling paradigm that the motor control people are just beginning to appreciate. So Bob mentioned in the preamble, Professor Noah Cowan from Johns Hopkins. We're building on a lot of his methods he developed with a PhD student, Itai Roth, and they've applied them to different kinds of animals, and we're in parallel with them applying them to people. But what's really powerful about this is I can take this picture and I can write out a set of equations that are implied about the relationship between the different blocks in these equations. And then because things are linear time invariant, or approximately so, I can algebraically manipulate those equations to solve for unknowns in terms of knowns. So in particular, we don't have a way to peer inside the person's brain and see what their feed forward and feedback controllers are. But what we can do is measure empirically their transfer function from the reference we apply to the input they produce, or the disturbance we apply to the input they produce. And then we know the model that we're applying, so we know it's inverse. So then we can do this manipulation algebraically to estimate the feed forward and feedback controllers. So we've done this in this kind of experimental paradigm where we have people with a one-dimensional manual input. This is basically just our 20th century revisiting of the Merkur experiments. They're trying to track this gold reference. They see their cursor position in purple. And then they're also, it's not represented here visually and it's not shown to them or really even told to them, but that disturbance is kind of invisibly perturbing their cursor position, and they need to figure out how to reject that so they can track the reference. And really quickly, we in our paradigm, in our specific experimental setup, we reproduced kind of known results where people do approximately invert system dynamics. So what you're seeing here are, if M is a first order system, so the person's commanding velocity, so then M inverse is plotted as a dashed line in these plots, then our estimated feed forward controllers in red, kind of approximate that inverse. Now people at low frequencies basically do, and the dots versus the fill are two different experiments. We did two different ways to estimate the same quantity to try to check for consistency and linearity and things like that. And at the lowest frequencies, so for the kind of slowest motions of the reference and disturbance, they do a pretty good job. And then at higher frequencies, they kind of hedge. Intuitively, this makes sense because if you are doing model inversion to determine a feed forward input and you get it wrong, in particular if you get the gain too high, then you will actually cause the closed loop system to be unstable, and you'll have to then fight that instability that you've introduced using your feedback controller. So it's not so surprising that people kind of hedge and don't fully invert, but it is a feature that we have to take into account if we want to predict how people are going to behave in any particular scenario. And the same story is basically true if people control a second order system. So if they're commanding acceleration, like they're driving a virtual car or other mechanical system. Okay, so that's kind of reproducing known results. And so here's the first of two results I want to show you that are fresh out of our group, new directions we take in this. First thing we did was we compared it with if you'll forgive me, a neural interface. So what we're actually measuring is surface EMG from biceps and triceps, which I call neural because it is a signal coming directly from the nervous system, not not at the output of a manual interface, and it's an electrical signal. Okay, fine, but I'll hedge and I'll call it a muscle interface. That's a little bit more common in the literature. So we do the exact same experiment. The subjects do the exact same experiment with a slider with the one-dimensional input, and then with this neural EMG interface. So we're basically taking biceps and triceps, heavily filtering it, processing it, and then boiling it down to one-dimensional input to supply to our game. And here's the kind of results we get. Actually very surprising to me. So if you look at tracking error, meaning how well do they do the task we told them to do, how well does their output track the reference, then actually there isn't really a statistically significant difference between muscle and manual interfaces for first order or second order systems. So they're basically as good at doing it with either or, which surprised me because I would have expected it's much more difficult to use this muscle interface that's using these very noisy signals that are very aggressively filtered, but that's not what we see. And if we look at inversion error, so how well do people implement the inverse of the system forward model? In the first order case, we see no real difference between muscle and manual. But in the second order case, we see a significant difference. They're actually much better at inverting the forward dynamics using the neural interface than they are the conventional manual interface. So this is kind of wild. Now, this could be specific to our setup. This could be specific to the systems that people are controlled. I'm not saying that muscle is always better than manual, but the fact that it happened in our experiment to me indicates a potential, kind of untapped potential for using alternate input modalities to control high performance robot systems, right? So the fact that people are doing a better job inverting a second order system means that if you wanted to steer a quadrotor at a high speed through a forest, then you would probably prefer to have a muscle interface where they're able to produce those high frequency inputs to track the reference that they determine from their visual input, then you would, and then just reject the disturbances and errors and stuff like that through low level control, and not rely specifically on a manual interface. And then there's even bigger possibilities in potentially mixing these two. We could take all these measurements and then figure out the right way to fuse them together. I think that's a cool prospect. Okay, and then the second and last experimental result that I'm going to talk about, and I will end when I said at 5. Another thing we did was we said, okay, there's this thing called hand dominance, right? Everybody here probably knows that whether they're right-handed or left-handed, or at least knows what that concept is. Statistically, it's something like 70% of people are right-handed, 20% are left-handed, and the remainder don't really know, or they don't really care. They're kind of ambidextrous, or they don't make a big difference. So we were curious, okay, how much of a difference does handedness make in this experiment? So we recruited two populations of people. We divided them into two groups. One played the game first with their dominant and then their non-dominant hand, and then the other vice versa. It just so happened the groups that we recruited, it wasn't a selection criteria, were all right-handed, like they all reported being right-handed. And so I'm going to conflate dominant with right hand, even though in general that's not the case, but in our experiment it happens to be. Okay, so we can look at tracking error in this experiment as the two groups of subjects learn to play the game. And first, with the first hand, we see a reasonable sort of decrease in tracking error over time, right? People are learning to play the game. And then when they switch hands, kind of surprising to me at least, wasn't my expectation at all, that learned performance persists, right? So we're not seeing a resetting of the error going back up. It's not like they're just relearning from scratch with their other hand. They kind of keep going. Even more surprisingly to me, we see essentially indistinguishable learning curve with the non-dominant left hand initially, and again, no change when we switch. And so, if we look at the statistics from the first 5 and last 5 trials and we kind of compare them, yeah, there's a statistically significant decrease in tracking error with your first hand, regardless of whether it's your right or left or dominant or non-dominant hand, and then no change when you switch hands, and no further learning for the rest of the experiment. And there's also no change in the final steady state error between, regardless of whether you're using your dominant or non-dominant hand. So that's kind of wild. The hands are performing the same, and this learned controller transfers between the hands. So that's kind of an interesting thing we could exploit. And then the final kind of thing we could look at is, oh, well, how are their feed forward and feedback controllers changing? And this was also surprising because we designed this study anticipating that we would see significant adaptation in the feed forward controller, right? The idea being that especially when you're using your non-dominant hand, that it will take you a while to learn the system dynamics and implement the inverse. But in fact, we tried every which way. We could not find a statistically significant change in the feed forward controllers we estimated, whereas there was a marked and immediate change in the feedback controller when you used your first hand, and then no change when you switched to your second hand. So what these results suggest is that people are actually primarily adapting with their feedback controller and their feed forward controller. They basically walked in off the street. Now, granted, they were controlling a second order system, which, like, if you've driven a car, flown a drone, or played a lot of different video games, very common kind of system. So maybe we come in off the street with internal models of certain systems, and then when we learn to control, we actually just tune up our feedback gains or something like that. So I also think this is interesting that contrary to what has been shown in a different type of experiment, arm reaching, which is a different motion and engages different parts of the body and brain, we see this adaptation primarily in feedback and not feed forward. Okay, so 5 on the dot. Those are all of my results. The takeaway here is that, you know, we have this way of experimentally probing the controllers people use to interact with dynamic systems, and that they can use, you know, different hands, different modalities. They can use their muscles, potentially their brain. That's a direction that we're taking this with collaborators. So I think there's really kind of exciting potential to mash these up. And so for the people who are into this kind of inside baseball, my career proposal that I submitted is to mash these 2 ideas up. So that's hopefully the future of my lab in the coming 5 and 10 years. And I'll just take 1 minute selfishly to shamelessly plug a seminar series that I'm hosting this quarter. So my department's UW ECE Colloquium this fall is around the theme of this talk. I basically invited, I would love to say all my friends, but really what I can say is one close friend, Ram Bazadevan, who's also a Berkeley grad, and then a bunch of people that I look up to in the community and whose work I've followed very closely, you know, my entire career. And so it's a real pleasure and honor to be able to host them and have their talks. And this is all open to the public. You can attend synchronously if you sign up for a mailing list and get our Zoom links, or you can just go to YouTube. The videos will generally be posted within about a week of the talks happening. So I'd be really happy to share that with you. So with that, I'd like to acknowledge, of course, the contributions of this wonderful team of collaborators that I've built up at my lab at UW and other collaborators around UW, and, you know, friends from familiar faces from Berkeley and people who've moved on to bigger and better things, and of course the funding agencies that make this work possible. None of this would be possible without all of these other contributors. So thank you very much for your time. I'd be really happy to take any questions you have.
All right, thank you so much, Sam.